In 1833, the City of Baltimore passed an ordinance that prohibited steam locomotives from operating within city limits. Horses were to pull the railcars through town. The locomotive would wait at the boundary. This was not a fringe position. Over the following decades, dozens of American and European cities passed similar restrictions. Steam locomotives were banned from city centers, limited to specific corridors, required to operate below walking speed, or prohibited entirely within defined boundaries. The machine that was simultaneously shrinking continents and building industrial economies was being thrown out of the very cities that depended on it. And the reason wasn't politics, and it wasn't economics. It was noise. It was smoke. And it was the specific, visceral danger of putting a machine producing 180 pounds per square inch of steam pressure into a street full of horses, pedestrians, and wooden buildings. The story of how cities tried to ban the steam locomotive, and how that conflict forced one of the most significant engineering transitions in railway history, is the story of how the railway industry learned that the machine that worked perfectly in the open countryside was a completely different problem in an urban environment. To understand what early steam locomotives were actually like in a city environment, you need to understand what they produced beyond motion. A steam locomotive running at full pressure exhausts steam through its blast pipe on every piston stroke, a sharp, rhythmic percussion that was described by contemporary witnesses as somewhere between an artillery piece and a thunderclap. At close range, a working steam locomotive produced sound levels that would today require hearing protection by law. The blast from the exhaust stack was not a gentle chuff. It was a physical concussion of sound that could be heard for miles and felt in the chest at close range. The whistle was worse. Steam whistles on early locomotives were not the carefully tuned instruments of later railway operation. They were high-pressure steam venting through a simple resonating chamber, producing a sound that contemporaries described as a shriek, a penetrating, high-frequency blast that could carry over long distances and that horses, in particular, found deeply alarming. Horses were not an incidental concern. In 1830, horses were the primary motive power for everything in a city, including carriages, freight wagons, omnibuses, and fire engines. A city street was a carefully managed ecosystem of horse-drawn traffic, pedestrians, and vendors. Introduce a machine that produced sudden, unpredictable concussions of sound and steam, and the result was horses bolting, carriages overturning, and people being trampled. This happened regularly, in multiple cities, in the early decades of railway operation. The smoke compounded everything. A hard-working steam locomotive consumed enormous quantities of coal or wood, and produced proportionate quantities of black smoke, hot cinders, and particulate matter. In an open landscape, this dispersed quickly. On a city street, between buildings, it did not. Early railway operations through city centers left residents and businesses coated in soot and coping with visibility that resembled a coal mine. And beneath all of this was the fundamental danger of the machine itself. A steam boiler operating at high pressure in the early decades of the Industrial Revolution had a meaningful probability of catastrophic failure. Boiler explosions were a regular feature of the 19th century industrial and transport news. A boiler explosion in the open countryside killed the crew and damaged the locomotive. A boiler explosion in a city street was a different category of event entirely. Cities were not being irrational when they tried to keep these machines out. The restrictions took different forms in different places, but the underlying logic was consistent. The steam locomotive was acceptable at a distance. It was not acceptable in the middle of a city. In New York, the solution was a boundary. Steam operations on the New York Central Railroad were eventually restricted from operating south of a specific point on Manhattan Island. Trains from the north arrived at a terminal at the boundary, where steam locomotives were uncoupled and horse teams pulled the passenger cars into the city. This was inefficient, expensive, and slow, but it was the accommodation the city demanded. In London, the Underground Railway that opened in 1863, the world's first, was built as a steam operation, running through tunnels below the city streets. This created conditions inside the tunnels that passengers and staff described in terms that make modern subway complaints sound trivial. The tunnels filled with steam and exhaust gases. Visibility dropped to near zero. Ventilation shafts were cut through the streets above, producing spectacular, if alarming, eruptions of steam and smoke at street level. Staff working in the tunnels regularly suffered respiratory problems. Passengers were advised that the atmosphere had medicinal properties, a claim made with uncertain conviction by railway promotional materials. The underground steam operation worked, technically, but it made clear that steam traction had a ceiling in urban environments that was going to be increasingly difficult to push past. The event that forced the issue in New York, and that directly produced one of the most significant railway engineering projects of the early 20th century, happened on a January morning in 1902. A New York Central Express train was running south through the Park Avenue Tunnel toward the old Grand Central Depot at 42nd Street. The tunnel was filled with steam and coal smoke, as it always was. Visibility for the locomotive crew was essentially zero. The train passed a signal at danger, a signal telling it to stop because the track ahead was occupied. The crew either did not see the signal or could not stop in time. The express ran into a standing commuter train ahead of it. 15 people were killed. Dozens more were injured. The investigation was unambiguous. The tunnel atmosphere had made it impossible for the crew to operate safely. This was not an isolated incident of human error. It was a predictable consequence of running steam locomotives through enclosed underground spaces in a city. The New York State Legislature responded by passing a law banning steam locomotive operation south of the Harlem River in Manhattan, effective from 1908. The New York Central Railroad had 6 years to electrify all operations into Grand Central Terminal. The alternative was to stop running trains into Manhattan entirely. The electrification project that followed was, at the time, the largest railway electrification ever attempted. The entire terminal complex had to be rebuilt. New electric locomotives had to be designed, tested, and delivered. The existing steam infrastructure, including water columns, coal facilities, and ash disposal, had to be torn out and replaced with electrical substations and conductor rail systems. The new Grand Central Terminal that opened in 1913, the building that still stands today, in use over a century later, was designed from the beginning around electric operation. 2 levels of tracks, both underground, handling 67 platforms. No smoke, no steam, no blast of exhaust on every stroke. The contrast with the old depot was immediate and total. Passengers arrived in a building that was clean, quiet by the standards of the age, and lit by electric light. The acrid fog of steam locomotive operation was simply gone. But the more significant engineering consequence was what electrification made possible underground. Without the constraint of keeping steam and exhaust gases out of enclosed spaces, the entire terminal could be built below street level. The streets above could be reclaimed. The Park Avenue Viaduct, the elevated structure that had carried the steam railway into the old terminal, was replaced by a tunnel beneath one of Manhattan's most prestigious avenues, and the property above was developed. The economic value created by electrification was, in retrospect, staggering. The ability to sink the railway underground transformed the real estate around the terminal entirely. The technology that made all of this possible was the electric traction motor, the same fundamental technology we've discussed in the context of diesel-electric locomotives and mining trucks. But in the early electrification projects, there was no diesel generator on board. The power came from a central generating station, distributed through conductor rails or overhead wires, and consumed directly by motors on each locomotive or multiple-unit car. This arrangement had been demonstrated on a small scale since the 1880s. Frank Sprague's Richmond Union Passenger Railway, opened in 1888 in Virginia, was the first successful electric streetcar system, and it proved that electric traction could handle the starting loads and grade changes of urban operation reliably. Scaling this to heavy mainline railway operation was a different challenge, and the electrification projects of the early 20th century, New York Central into Grand Central, the Pennsylvania Railroad into Penn Station, the Chicago Elevated Railways, were engineering undertakings of the first order. The generating capacity required was enormous. The distribution systems had to operate reliably in all weather. The locomotives had to perform comparably to the steam power they replaced on demanding schedules. They did, and in most cases, they exceeded it. Electric locomotives had the same fundamental torque advantage as the diesel-electric systems that would follow them: maximum tractive effort at zero speed, controllable power delivery across a wide speed range, and the ability to return energy to the system during braking. They were cleaner, quieter, and required less maintenance than steam. In urban environments, they were simply a better machine. The steam locomotive that was banned from Baltimore in 1833 and restricted from Manhattan in 1908 was not a failed technology. On the open main line, across the prairies and through the mountains, it remained the dominant form of motive power for decades after urban electrification had made it obsolete in city environments. But the conflict between steam traction and the urban environment produced something more significant than a series of local ordinances and workaround arrangements. It forced the railway industry to develop and prove electric traction at scale in the most demanding operational environments available, decades before diesel-electric technology would have made the question academic. The engineers who electrified Grand Central Terminal were not trying to invent the future of urban transit. They were trying to solve a specific problem created by a specific law passed in response to a specific accident in a specific tunnel. But the technology they proved in that project became the foundation for every subway system, every commuter rail electrification, and every urban transit network built in the century that followed. The machine that was too loud and too dirty for the city forced its way out of the city, and in doing so, produced the engineering that now carries millions of people through those same cities every day, silently, underground, without a trace of steam.